In this section, we will discuss the rank and the row space of a matrix A. By definition, the row space is the set of all linear combinations of the rows of A. So just like we did in the column space, we take the span of the rows and that will give us the row space. So here we have a matrix A, and notice that we've written the row space as the span of the rows of A, where the rows have been written with the elements having commas between them. This is actually equivalent to writing these rows as columns, so we could also write it in the following way. So here we have written them as vectors, so either of these ways of writing it is appropriate. We can also see from this example that the row space of A is equivalent to the column space of A transpose. So here we've written the matrix A transpose, and notice if I find the column space for A transpose, I get exactly the answer that we got here. The following theorem tells us how to find the basis for the row space of a matrix A. So notice first that the title says that row equivalent matrices have the same row space. Now this is not true for the column space. So it says here, if I have a matrix A that is row equivalent to B, then the row space of A and the row space of B are the same. And if B is in row echelon form, the non-zero rows of B form a basis for A and for B. So here is the same matrix that we looked at previously, where we found the row space of the matrix. And now we're going to find the basis for the matrix, the basis for the row space. So all I've done is taken this matrix and put it into row echelon form. So in row echelon form, we generate this matrix B. So according to the theorem, the basis for the row space are the non-zero columns of the matrix B. I'm sorry, the non-zero rows of matrix B. So that would be the first row and the second row. So according to our theorem, the basis for the row space is the set of vectors 1, 2, 3, 4 and 0, 1, 2, 3. Again, the basis for the row space would be the non-zero columns for B. So the non-zero rows for B. So the rows that we have here that contain zeros would not be included in the basis. So again, this is the basis for the row space of A, which we label row A. Notice that in this case, it is not appropriate, as we did in the column space, to go back and choose the first row of A and the second row of A to be the basis for the row space of A. Now this might seem counterintuitive because we did that for the column space. Here is why. I've relabeled these bases B1 and B2 because I don't want you to confuse them with the matrix B that we have here. So again, B1 is the basis for the row space of A, and I want to show you that B2, which are the first two rows of A, does not form a basis for the row space of A. First of all, notice that the second element is twice the first, so this does not even form a linearly independent set. So it turns out that when I performed row operations, there was an exchange of row 2 with row 3. Right, so because of that, the rows have moved location. So you don't want to go back to the matrix A to find the row space. You always want to take it from the matrix B, and that is the matrix in row echelon form. So again, this B2 would not be a basis for the row space of A. So now let's go back to our theorem because we'd like to understand why it is true that the row space of A is equivalent to the row space of B. So here is why. First of all, the rows of B are simply linear combinations of the rows of A if we simply perform row operations on A to get B. So we say the rows of B are linear combinations of the rows of A. Let's talk about what elementary row operations actually do to a matrix. So there are three different types of elementary row operations that we would have. One is a row scaling, when we simply take a row and multiply the row by a constant, say k. Another one would be an exchange of two rows, or an interchange of two rows. And the last one is a row replacement, where we take a multiple of one row and add it to that row, to another row, sorry. So really, elementary row operations just are linear combinations of the rows of A. And so if we think about what row space means, which is the span of the rows, right? So the row space is the span of the rows of A. If I simply perform linear combinations on the rows of A to get to B, then the span of the rows of A is equal to the span of the rows of B. Hence, the row space for A and the row space for B are the same. Now on to the definition for rank. The rank is simply the dimension of the column space of A. So you see the notation here, and if you recall, dimension means the number of vectors that are in the basis. So the rank is the number of vectors that are in the basis for the column space of a matrix A. In this example, we're going to find the basis for the row space and the column space, and then find the rank of the matrix A. So we've taken A and we've found the row echelon form for A, which is given here. And we want to find the basis for the column space. So notice in reduced form, there are two pivot columns, and the pivot columns of A form the basis. So again, we don't go to the reduced matrix, we go back to the original A. And so the basis for the column space is made up of those two vectors. Here we have the basis for the column space, which again we said was just the first two columns or vectors in the matrix A. Now let's talk about the basis for the row space. So for the row space, we need the non-zero rows of the reduced matrix. So that would be the row here and here. Sorry, I missed that one in there. It should be included. All right, so now let's write the basis for the row space. And we have it. Here is the basis for the row space of A. So now what about the rank? So remember, the rank is the dimension of the basis for the column space. There are two vectors in the basis, so we know that the rank of the matrix A is equal to 2. It is no coincidence that the number of vectors for the basis for the row space and for the basis for the column space are the same. Both of them have a dimension of 2. The rank theorem tells us that the dimension of the column space is equal to the dimension of the row space. So if you recall this matrix A, in reduced form we had two pivot columns. So notice that the number of pivots also indicates the number of non-zero rows of the matrix B, right? So this is B, the row echelon form. And that tells us the number of vectors that are in the basis for the row space. So any row that does not have a pivot is going to be a row with zeros. So that means that the number of pivot columns is equal to the number of rows with pivots. So this makes sense. Additionally, the rank theorem tells us that the rank of A plus the dimension of the null space of A is the number of columns of A. So why is that true? the rank of A is the dimension of the column space. And we know that the number of vectors in the column space is going to be equal to the number of pivot columns in the matrix. The dimension of the null space is related to the number of free variables that we have, and hence is the number of non-pivot columns for a matrix. And so if we take the sum of the non-pivot columns and the pivot columns, then what we end up with is the total number of columns in the matrix A. Here are some examples of how we can apply the rank theorem. So let's look at the first example. It says that we have a matrix A, and A is 7 by 9. It has the dimension of the null space equal to 2, and it asks us to find the rank of A. Recalling what the rank theorem says, it says that the rank of A plus the dimension of the null space, or the nullity of A, is equal to the number of columns of A. So we know that the dimension of the null space is 2, and we know that the number of columns of A are 9. So this tells us that the rank must be equal to 7. In other words, the matrix A has 7 pivot columns and 2 non-pivot columns, which gives us 9, or the total number of columns in the matrix A. The next example is a bit tricky. It says, can I have a matrix that is 6 by 9 that has the dimension of the null space equal to 2? So let's set up our equation using the rank theorem. The null space is 2, or the dimension of the null space, so the nullity is 2. The number of columns is 9, which tells us that the number, or the rank, or the number of non-pivot or pivot columns must be 7. So here is why there's a problem here. Notice that our matrix is 6 by 9. That means that it only has 6 rows. So the most pivot columns that I can have would be 6 and not 7. Because remember that each row has to have a pivot, and we know that the dimension of the column space of A is equal to the dimension of the row space of A. So I would need 7 pivots, but I only have 6 rows. So this is not possible. So we'll say no. Okay, so here it comes, the invertible matrix theorem again. So let's talk about how these ideas of the column space and the null space all relate back to invertible matrices. So again, we have an n by n invertible matrix A, and the following statements, and actually these are included in the other one, so this is like an addition to the ones we already have. So if one of these statements is true, then all of them are true. So the first one says that the columns of A form a basis of Rn. Well, why is that true? Well, A has n pivot columns if it's invertible, which means that Ax equal to 0 has only the trivial solution, which tells us that the columns of A are linearly independent. So we also need to show that for it to be a basis that the columns of A must span Rn. Well, again, we have n pivot rows, which tells us that there is a solution for every B in Rn to Ax equal to B. So we have both conditions, that the set is linearly independent, or the columns are linearly independent, and that they span Rn, which tells us it is a basis. The second one says that the column space of A is equal to Rn. Well, the column space is simply the span, or all possible linear combinations of the columns of A. So again, we said that Ax equal to B has a solution for every B in Rn, which tells us that indeed the column space of A, or that all possible linear combinations, will give us everything in Rn. The next one says that the dimension of the column space is equal to n. Well, this is easy, right? The dimension of the column space would be the number of pivot columns of A. Since every column has a pivot, then there are n of them. And the rank of A is in, well, this is just the definition of the column space, or the dimension of the column space, which is the rank. If you go to the next one, it says the null space of A is equal to the 0 vector. Well, AX equal to 0 has only the trivial solution if every column of A is a pivot. Hence, we know that the only solution to AX equal to 0 is the 0 vector, which would give us the null space. And lastly, it tells us that the dimension of the null space is equal to 0. Well, if every column of A has a pivot, then there are no non-pivot columns, so the dimension for the null space must be equal to 0.